Here we have some materials, it's like a wire or so, and I'm going to apply a force to it across a cross-section area of the wire there. And what I've done is applied a stress or tensile stress, which is a force per unit area. So it's given this symbol here, sigma, and that's the tensile stress in pascals. The force is in newtons and the cross-section area is in meters squared. So, for example, a stress of 220 megapascals would mean 20 million newtons of force applied for every meters squared of area of the material. So this is a typical type of stress applied to a wire because the cross-section area of wires tend to be quite small. And the cross-section area can be circular, like in this case, where so we'll use the equation pi r squared for the area, or it could be a rectangle, or it could be a triangle, or maybe even a trapezium. Okay, let's say the original length of this wire was L, and by applying a force, we cause it to extend by delta L. So what we've done is we've created a strain here, or tensile strain. Tensile just means stretching. So the strain here is the fractional change in length. It's a useful quantity and is given this symbol epsilon, and it's delta L over L. And so tensile strain made from the change in length at the top there, which is measured in meters, and the original length, which is measured in meters. So if you have meters divided by meters, then the units cancel out. So tensile strain actually has no units. An example of tensile strain, let's say for example 0.10, which basically means a 10% increase in the length compared to the original length. So in other words, it'd be 110% final length compared to the original length. A useful quantity we can get from using stress and strain is Young's modulus, which is stress divided by strain, or stress per unit strain. Now, stress we saw is force per unit area and is measured in pascals. Strain is unitless because it was a change in length over length, so the units cancelled out. And so therefore, the unit for Young's modulus, which is also going to be pascals. So Young's modulus is really useful because it's a property of the material. So it tells us about, for example, copper or steel and what the material and how easy it is to stretch or to be honest, how stiff it is. The higher the Young's modulus, the more stiff the material. So for example, Young's modulus of steel is around 200 gigapascals. So that means you need 200 gigapascals of stress in order it needs to be applied to the steel in order to get a strain of one. So in other words, double its original length. So here's the equation for Young's modulus, where E actually represents Young's modulus, which is very confusing because capital E also represents energy. So instead of using capital E, I'm going to actually use Ym instead, and that's stress over strain. So the equation can be written as also stress divided by strain. So stress is force over area, strain is change in length over length, and when you're dividing two fractions like this, you flip the second one over and you multiply the first one. So I've flipped over, so it's L over delta L Z, and that gives you this very useful equation. Here's a table with the Young's modulus of various materials. Notice how the units for Young's modulus is in gigapascal, so that's 10 to the 9 pascals. And this is typical because a large amount of stress would be required to stretch these objects. And so diamond's got the highest, so diamond has got one of the highest there, so it's very, you need a lot of pressure in order to change its length. And then after that, we've got steel. Then in between, you've got bone, and then you've got rubber, which stretches a bit more better than the others, which requires less stress to get the same amount of strain. Okay, we have an example question here. The support cable on a bridge has a diameter of 9.8 centimeters and a length of 40 meters. It is made from high tensile steel, which has a Young's modulus of 280 gigapascals. The tension in the cable is 7.0 times 10 to the 5 newtons. Calculate the tension in extension of the cable. Okay, so I'm going to draw, it's a cylinder because the word diameter gives it away. The cross-section area is a circle and the length is 40 meters. So I'm going to label that on. So I've got the diameter 9.8 times 10 to the minus 2 and the length is 40 meters. I'm going to find the cross-section area because I know you have to use that to find the stress first. So pi r squared. So take the diameter, make sure you divide that by 2 and notice how I've turned the diameter from centimeters into meters. And so I've got an area here, 7.543 times 10 to the power minus 3 meters squared. Then I'm going to write down the equation for Young's modulus where I've already done the stress divided by strain and I've arranged it correctly. And because I want the extension delta L, I'm going to bring that to the left-hand side and I'm going to bring Young's modulus to the bottom. So the equation looks like this. Okay, so let's start filling it in. So first of all, force 7 times 10 to the 5 times the original length 40 meters and then divide it by the area which we calculated just previously and then finally the Young's modulus. And this gives us a change in length or extension of 0.013 meters. You can find the Young's modulus of various materials using a setup similar to this one here. So in this example, I'm going to use copper wire and I'm going to lock it between these wooden blocks so it's tied down and it's kept attached on the right hand side there. Then I'm going to pass, first I'm going to actually attach a mark over here. I'm going to pass it over a pulley which is attached to a table over a clamp. And actually before I even add a mass, so this is before I stretch it, I'm going to measure the original length. And I'm going to measure it from where it's attached to the wooden block on the left hand side of the wooden block there, all the way to the marker. That's the original length. Then also before I stretch it and by adding a mass, I'm also going to measure the diameter using a micrometer at different points using different orientations. So I get an average of all those. And using that diameter, I can find the cross-section area of the wire. So pi diameter squared over 4. So now I've got the cross-section area, I've got the original length. I'm going to apply a mass on the left-hand side there. So I'm actually going to attach the mass now. And the mass is going to apply a force. So I can calculate the force by using F equals mg, so the weight basically. And that is going to cause it to extend. So when we apply this weight, watch the marker is going to stretch. Okay, so you can see it's stretched now. We've got an extension. So we can record the marker's position before and after and get the extension from that. Then we can just put these numbers into the Young's modulus formula to calculate the Young's modulus of copper.